Hello kids! In this video, we will discuss volume by slicing. So for my students, you should have watched the first video first, which is the video about volume of solid of revolution. In that video, what we did is starting with a plane region, we revolve that region with respect to an axis of revolution to obtain a solid. For this one, we will consider an arbitrary solid and let's try to identify its volume. So consider this solid right here. One method that we can do is slice a solid and obtain the volume of each slice. So looking at this slice right here, for example, this one, we have two components which is similar to the washers method that we did. First is your cross-sectional area right here and the height of your slice, which is h. So the volume of this one would be A multiplied by h. Then once again, to obtain the volume of the entire solid, we just add up all of this A times h. And so, if we will set that one up, our volume would be the integral of the area multiplied by the height. So you have your area multiplied by the height, starting from the leftmost point to the rightmost point. Now let's look at what the height will be. Observe that we are slicing vertically, and so our height would be this one right here. This is your area and this is your height. And your height is a horizontal distance, which means that this is an x value. This would be a value in terms of x. So your height here, we can denote this one by dx. So our height right here would be dx. And since we are using dx for height, we have to make sure that your area right here would be an area in terms of x. So this a right here would be a of x. So your area should be a function in terms of x. And we are doing this from the leftmost point. So let's say the leftmost point is x equals a. Then the rightmost point is x equals b. So we are doing this from x equals a until you reach x equals b. That is for you to span this entire solid right here. So we have from x equals a to x equals b. So this is the volume of slicing, but by vertical slicing. So once again, if you have vertical slicing, that means that your height is horizontal. And if your height is horizontal, that means we are spanning this solid right here through x values. For this one, what we did is to slice horizontally. So this one is horizontal slicing. In horizontal slicing, we have the same technique. You have your area right here and you have your height. Your height here now is a vertical height. So that means this is spanning through values of y. So we have dy right here. And so your area right here should be in terms of y. So for your volume, that would be the integral of area times height. So that's a of y times your height, which is dy. And to span the entire solid right here, we are starting from the bottom part to the top part. So for example, if the bottommost is y equals c and the topmost is y equals d, that means that we are slicing horizontally, and we are obtaining the volume starting from y equals c until you reach the topmost part of your solid, y equals d. So that's from y equals c to y equals d. Okay, so once again, for vertical slicing, that means you have a horizontal height, and horizontal height, that means for us to span the entire solid, we are moving through x. While for the horizontal slicing, you have a vertical height, and vertical height, that means we are spanning through values of y to span the entire solid. So that means we are moving through values of y. Let's proceed with a simple example. Let's determine the volume of a right triangular cone with radius r and height h. The challenge here is we have to identify whether we will do a vertical slicing or a horizontal slicing. Let's try first what would happen if we will slice this solid vertically. So for example, if we slice it exactly right here, what do you think will we get? So what we will get here is a triangle, right? What we will obtain is a right triangle. It's a triangle right here. However, if we slice right through here, what do you think will happen to our cone if we slice right here? Can someone figure it out? What you will actually get is something parabolic, like this one. Oops. What you'll get is something parabolic like this one. This is actually a big problem for us, since depending on where you slice, you have different cross-sectional figures here with different areas. Luckily for this one, it's quite easy to obtain the area. But for this one, it would be a little bit difficult. So let's not do this one. Instead, let's try a horizontal slicing technique. If we slice right here, let's say, what you'll get is a circle, right? If you slice here, you'll get a circle. If you slice right here, you get a circle. If you slice at the very top, what you'll get is a point, but you can think of points as circles of radius 0. So what we have demonstrated is whatever you do, as long as you slice horizontally wherever you want, what you'll get is still a circle. So what we'll do here is slice vertically, slice horizontally, and slicing horizontally, that means that we have a vertical height, and vertical height, that means that we are moving through values of y. Let's start with the very simple slice that we know right now. This one right here. So what we know is that our right triangular cone has radius r. So if we draw right here, you have a radius r. And this happens at the very bottom, or that's when height equals 0. Or y equals 0. But if we slice arbitrarily right here, so that means for any y, from the very bottom, y equals 0, to the very top, recall that our cone has height h. So that's y equals 0 to y equals h. So for any y in this interval, 0 to h, what we still have is a circle, but our problem is our radius is also arbitrary. We don't know what the radius is. But since our goal is moving through y, we need to set up our integral in terms of y, and so our goal is to write this radius in terms of y. How could we possibly do this using our given values right here? So let's start again with your y equals 0. So at y equals 0, you have radius r, and the height of h. Radius r and a height of h. If you slice your cone in this manner, vertical like this, and horizontal like this, what you'll obtain is a right triangle. What you'll obtain is a right triangle with base r, and height h, right? Now let's try to do this arbitrarily. So for example, I slice right here. I'll take this y value here. If I take this y value here, okay, I'll just use orange instead. If I slice right through here, at whatever value of y, I'll have a base here of r of y, which is just like what we said a while ago. As for our height would be this entire h. However, we are removing this portion right here. But this portion right here is from this value of y to 0. So this is a length of y. And so this entire thing here, this one right here, should have a value of h, but we are removing this height of y right here. So we have h minus y. And so for any value of y, we are sure that we have a radius of r of y and a height of h minus y. One good thing that we know about this one is that we have a right angle for both of them. And as you can see, the triangles that we are forming, it will always have the same angle. Why? We are taking from the same slanted line, and we are taking from the same vertical line. So by what we know in geometry, this one would have the same angle. So this one have the same angle right here. And so what we have are similar triangles. These two are similar triangles. And by what we know about similar triangles, we can relate the value of their sides. So for this one, we can talk about the ratio between this line right here, the length of this line right here, and the length of this line right here. So by similar triangles, we have h over r, that the length of this one divided by the length of this one is equal to the length of this one divided by the length of this one. So that's h minus y all over r of y. And by solving for r of y, we get the form of the radius that we want. So cross multiplying this one, we get h times r of y equals r times h minus y. And finally, dividing both sides by h, we obtain r of y equals r times h minus y all over h. And so, the setup for our volume would be the integral of the area of your cross section. So your cross section is just a circle, and so the area of this one is pi times r of y squared. So that's pi times r of y, which is r times h minus y all over h squared. And since our radius is in terms of y, we are integrating with respect to y. And for the bounds, recall that what we did is a horizontal slice. And so for us, the entire we are moving from y equals 0 until we reach the very top, which is y equals h. So this one would be from 0 to h. Now let's try to solve this actual integral. Let's do it in a different page. So I'll copy this one. What we have here is v equals pi times r times h minus y all over h raised to 2 dy. Note that we can distribute this square into each factor right here. So we will get integral from 0 to h of pi times r squared times h minus y squared all over h squared dy. As you can see here, you have a constant coefficient pi. And in this part right here, we know that r and h are constant. So we have constant factors right here. So we can put this entire thing outside our integral sign. We have pi times r squared over h squared integral from 0 to h of h, oops, sorry, h minus y squared dy. There are two ways for us to solve for this one. First one is distribute the square, and or should I say expand this term right here. So that's the first method. For the second method, observe that the derivative of this one is -1. And so we can do a u substitution, since -1 we can find it somewhere in our integral. So if we let u to be equal to h minus y, then we get du to be equal to -1 times dy, or negative dy. But in our integral, what we only have is a dy. So for us to obtain dy, we divide both sides by -1. So we get dy equals negative du. Take note, however, that in doing a u substitution, if you have bounds right here, you need to change them accordingly as well. So if y equals 0, that means that your u equals h minus 0 equals h. And if your y equals h, then your u equals h minus h equals 0. And so your integral will look something like this. You have pi times r squared over h squared times the integral. So the y equals 0 here will be changed to u equals h. And your y equals h will be changed to u equals 0 of h minus y. This is your u. So you have u squared, and your dy would actually become negative du. This one we can further work out into negative pi r squared over h squared integral from h to 0 of u squared du. And this one is just easy. So you have negative pi r squared over h squared multiplied by the integral of this one, which is u cubed over 3, u raised to 3 over 3. But you're evaluating this one from u equals h to u equals 0. So what we have right here is negative pi r squared over h squared multiplied by, first we plug 0 here. We have 0 cubed over 3 minus, we will plug h to every u right here. So we have h cubed over 3. This one right here would just be 0. So that's 0 minus h cubed over 3. And that's negative h cubed over 3. We have here negative pi r squared over h squared times negative h cubed over 3. And simplifying this one, you have h cubed divided by h squared. You'll be left with h. Then a negative times a negative would give you a positive. So you have here your 1/3. Your 1/3 is this one. Then you have your pi r squared h. And from your elementary days or your grade school days, this is your volume of a right triangular cone. I'm sure all of you are familiar with this one. And that's it for this example. For those who are watching this video that are not my students, you can comment in the comment section your questions. But for my students, you can message me through the messenger or through email. And for my students, I am glad to say that this is the end of Math 21. Congratulations for making it to the very end of this subject. If you have any questions, once again, you can comment in the comment section, or for my students, you can message me. Thank you and goodbye.